Hello everyone. So during the last lecture, it was lecture number 3 in 2 parts. We covered the basics of circuit analysis, and from this point on, all the way to the end of these lectures for this first circuit analysis course, we're going to practice the same rules or algorithm with circuits that have different number of components and different variety of components, and the approach is going to, for the most part, is going to stay the same. I've actually kind of abstracted the approach, the 3-step algorithm, to remind you what that approach was. I'm going to keep it on the corner here, and most likely I'm going to keep it in the corner throughout the semester and show you that we can always use the same technique and apply it to any circuit from now on and analyze the circuit. So what's going to be different time to time, every time that we discuss something, want to discuss something new, is mostly the equations for components. In other words, every time that we introduce a new electrical component, we have to understand the physics that governs the operation of that component, and next turn that physics into an equation that relates the physical parameters, and most importantly, the current that is passing through the component and the voltage across the component to each other, or gives us a function that describes how those parameters change. So with that, let's start with simple circuits and start with the most important components first. And these components are the most common in circuits, and then we take it from there. So the first kind of component that I want to introduce to you, and we've already seen those in other courses, and this would be kind of a repetition of what you've seen before. There shouldn't be anything majorly new here, or the sources. So sources of energy, basically. So they come generally in 2 different flavors: sources of voltage and sources of current. Now, in both cases, they basically source, I'm going to say source energy in the middle, but we categorize them into the 2 different kinds of voltage and current. Fundamentally, they are the same. So to symbolize these devices, you can think of two different symbols that are used here for the voltages, and 2 kind of symbols that are used here for currents. And I'm going to explain to you what the difference between the 2 are. So these kind of sources with a circle and a plus minus symbol for a voltage source are called independent voltage sources. Now what that means is that the voltage across this component, from the positive or higher potential to negative or lower potential, is a value that is not dependent on anything else that is going on in the circuit. So there is a voltage, we're going to call it Vs, that is assigned to this source, and that basically this value tells you what's the potential difference between the positive and negative terminal in this component is, and that is not a function of anything in a circuit. Whereas in the other kind of source, which are generally called the dependent voltage sources, the same voltage is actually a function of voltages and currents in the circuit. So these are dependent voltage sources, where the dependency comes from the fact that this voltage is not independent and rather is a function of voltages and currents that are in the circuit. So with the same kind of approach, we have the independent current sources, where again this source has a known current passing through it, and that value is not a function of anything in the circuit. And we have dependent current sources where the current is a function of voltages and currents in the circuit. I have to redo this went out of my, so the current of the source is a function of voltages and currents in the circuit. And that's it. This is all we need to know about these sources. What they're doing for us is that they're giving us a known value for the potential difference between the two terminal in the case of a voltage source, or a known current passing through the two terminals in the case of current sources. So if I want to write basically an equation that describes the functionality of these, it would be quite simple. So let's do it. I'm going to define nodes here, and in both cases I'm going to call them V1 and V2, V1, V2, and then have currents passing. I'm going to call it I, I'm going to call that I, and here the same thing, V1, V2, V1, V2, current passing through the component. Notice I'm doing the same thing that I would do when I label the circuit for this component, right? So I'm defining nodes, and then I'm defining node voltages, and I'm defining currents passing through the component. Now, if I want to write equations for any of these, the equation for this component, for the independent voltage source, would be V1 minus V2 is equal to Vs. Same here, V1 minus V2 is equal to Vs. Now, the only difference is that here Vs is a function of other voltages and currents in the circuit. In this case, I1 is equal to Is, same I, there's no I1, it's actually I. So I is equal to Is, and here I is equal to Is. These are the equations for these components. Okay, so I told you that when you reach to this point, you have to start counting the number of components in your circuit and then write an equation for them. And I think that these equations for the sources are quite intuitive. There are sources of voltage, so they're giving us a known voltage. That's all you need to know about them. So this equation basically just describes the same thing in the language of math. It tells you that the voltage difference across this source of voltage is a known value. V1 minus V2 is Vs, the same here. And this one says that the current that is passing through this component is a known value, a known given value in both cases. Notice that in the case of sources, the equation doesn't necessarily relate the voltage and current to each other. This is in the case of a voltage source, is just simply a statement about the voltage or the potential difference across the component, and in the case of a current source is a statement about the current passing through the component. So that's why I'm making the differentiation between writing an equation for the component or writing an equation for voltage and current. These are not equations for voltages and currents. These are equations for components that define the physics of that component. In this case of a voltage source, is just a statement about the voltage difference across. In the case of a current source, is a statement about the current passing through the component. So keep that in mind. Again, when you're seeing any questions in any of the exams or quizzes in the class, if you happen to not remember what the equation for a component is, just ask, I'll give it to you. But generally speaking, I assume that if you practice this is enough, and considering that this is quite an intuitive concept, you should be able to remember this. Now, beyond this, which is a simple component, I'm going to define the second simple component, which is a resistor. So, resistors. Now, the equation for the resistor, we already discussed that. It is something that we called it Ohm law. The symbol for the resistor is this. If I define V1 and V2 as the node voltages on the two ends, and then I as the current that is passing through, the equation for this component would be I, the current passing through the resistor. Let's actually call that IR. Again, this is going out of my window. So IR. So IR is equal to V1 minus V2, the voltage difference across, divided by the resistance. Now, to just make sure that you see how the convention goes, and this is obviously just a convention, you start, when you're taking a voltage difference, you start from the node where the current is coming into, and subtract it from the node where the current is coming out of. In other words, current goes from the higher potential toward the lower potential. And again, this is intuitive, higher to lower, right? It's remember the flat surface that I used as an analogy. So higher potential, lower potential, higher energy, lower energy, and that should be intuitive. And this is something that we normally call Ohm's law. I'm going to call that the equation for the component resistor. The same thing. So with those definitions, equations for components, now there are a variety of important circuits that we can start analyzing, and I'm going to start showing you some examples of those and how they are analyzed. Keep that in mind. I'm going to put an example here, simple example, and then try to do more complicated examples. So I'm going to call this R1, R2, and this would be V. So let's start analyzing this circuit. Again, to recap, analyzing a circuit means that we're going to calculate all the voltages for the nodes and all the currents passing through the components in order to be able to calculate all the powers or energies generated or dissipated in that network of components connected to each other. So we're going to start by labeling the circuit first, which was basically three-step on its own. We had to identify nodes. So this is one node, right? This is another node, and this is another node. Ends of components, if you recall. Then we're going to call them names. Now, this is V1, that's V2, and then we said one of the nodes we're going to take as ground. It's usually a good idea for the lowest potential in your circuit to be assumed as your ground or zero potential. And in a circuit like this, the negative terminal of your source would be the lowest potential. So you can take that as your ground or zero voltage. Now, does that matter? Not necessarily. You can actually pick any of the other two as your reference. and everything is going to work out fine. The actual values that you calculate for the potentials at that point are going to be different. Obviously, if this is 0, this is not going to be 0, but if I put my ground here, then that node is going to be 0 and this node is no longer 0. So the actual values change, but that doesn't matter. Voltage is a differential concept. Depending on where your ground is, the values might come out to be different. So I'm done labeling all the nodes. Now I'm going to start doing the currents. I'm going to say this is I1, this is my I2, and this is my I3. Done. Now I'm going to start writing KCL. So I have 3 nodes, 3 KCL. I don't have to do KCL for the node with the known value of voltage. So KCL. So that node, there's current I1 going into that node. So I1 is equal to the current going out of that, I2. For this node, I2 is going into that node. And then I3 is coming out. And last, for this one, I3 is going in and I1 is going out. Now, look at this. I1 is equal to I2. I2 is equal to I3. So naturally, you can see that mathematically speaking, I1 has to be equal to I3. So the third statement is really not adding anything to that first 2 statements that I wrote. Although all 3 are correct, this one is not necessary, so I didn't have to write that one. So that said, I'm going to remove it to avoid unnecessary complexity. So now, equations for components. Equations for components. How many components do we have? 1, 2, 3. There are 3 components in the circuit. The equation for this component, as we can see, necessitates that the potential from the positive terminal minus the potential for the negative terminal to be equal to the voltage of that source. So V1 minus 0 is Vs. For this one, R1, the equation is I1 is equal to V1 minus V2 divided by R1. For this one, I2, this one I3, voltage V2 minus 0 divided by R2. We're done. This is really all there is to be known about this circuit, and all it's left to do is to do the math. Relatively easy math for this one. You take V1, equate that to Vs in these other 2 equations. You also know that I2 and I3 are equal to each other, so the whole thing boils down to this. So Vs minus V2 divided by R1 is equal to V2 divided by R2. Vs is a known value. We have to repeat this. Vs minus V2 divided by R1 is equal to V2 divided by R2. So Vs is a known value, R1 is a known value, R2 is a known value. We'll just move these components around and I get an equation for V2. I'm going to write it down here. So V2 would be Vs times R2 over R1 plus R2. This equation right here lot of you may have seen this equation. It's called the voltage divider equation. This is a very common equation used in circuit analysis, and that's why it has its own name. What it tells you is that the voltage on that node is basically the voltage of the source divided between the two resistors proportionally, and it could be used to quickly calculate the voltage of that node without going through this process. I do not recommend remembering these equations, but I'm sure if you use these analysis and repeat this analysis often enough, eventually you're going to remember this, and that might be something useful to remember if that's something natural as opposed to just trying to memorize it. Okay, so we know voltage V2 as a function of Vs. We know V1, which is equal to Vs now, and we know what the currents are. Why? Because we know what V2 is and we know what V1 is. We just replace them here and we can calculate all the currents, which, as it turns out, all these currents obviously are equal to each other, and they're equal to Vs divided by R1 plus R2. This was just a simple example to show you that we can use these steps to calculate the currents and voltages for this simple circuit. So beyond what I explained here, I'm going to try to explain one more topic, and then we're going to finish this lecture and move on to more complicated circuits and other examples of circuit analysis using what we've learned. So with the definition of current and voltage that relate the two parameters in a resistor, you can actually come up with an equation that defines the power in a resistor. So let's look into that. If I define V1 minus V2 as VR, the voltage across, then the simple equation VR equal to RIR, which is the Ohm law, is going to evolve. We know that power in a resistor, in a component generally, so I'm going to put this here. So we know that power is equal to the voltage across the component times the current. Now in the case of a resistor, power of a resistor, the voltage across the resistor VR times, now I can use this equation for the current that is passing through, which is VR divided by the resistor. So the power of the resistor could be actually written as the voltage across the resistor to the power of 2 divided by the resistor. So what this equation does for us is that if I have the voltage across a resistor, I don't have to calculate the current in order to calculate the power. So I just skip a step. Take the voltage, square of that divided by the resistor is the power. There's a different also way of doing this. I can write the voltage as a function of current, which is the resistor times the current of the resistor times the current of the resistor, and that would be resistor times the current of the resistor to the power of 2. So again, then the value in this equation is that in a case that I have the resistance, the current passing through the resistor, I don't have to calculate the voltage across in order to be able to calculate the power. I just can simply take the current that is passing through, multiply it by itself, or a square of that, and multiply by the resistance, and that would be the power of the resistor. There's nothing new here. This just follows the simple equation that describes the resistance, but sometimes these equations are useful to speed up some calculations. They do give you some insight into the operation of the device too. And for example, for a given resistance, as you can see, the power that is consumed in the resistor is a function of the voltage to the power of 2. So if you want to increase the power that is consumed when you apply a larger voltage, the dependency is actually a square of that voltage, and the same with the current. The dependency is a square of the current that is passing through, as opposed to linear dependency. So that's something that might be useful too. That said, I'm going to end this lecture and move on to other circuits, using these components that we already discussed. And this would be, for the most part, what we're going to do for the second chapter of the book. Thank you.